Are we good? Okay, so today's dev meeting is going to venture off topic from web programming a little bit, just because I kind of ran out of things to talk about, and because I really enjoy doing 3D modeling and 3D kind of programming in general. That's what I wouldn't say a specialty, but what I enjoy. So going on to slide 2, the problem in a lot of different 3D games or simulations that you make is that terrain is often kind of difficult to make. Typically, what someone will do is you'll make an image that has a grayscale, uh, that they paint over on grayscale, so it's black and white and grays and whatnot, and that's called a height map. And then from that height map, they'll generate, the actual terrain. Well, a lot of times it's very difficult to get a good height map because it doesn't necessarily um, look like a real terrain, and even if you do the modeling by hand or whatnot, you end up with these kind of weird lumps and this and that, and it just kind of looks bad, and so the solution to this problem is that you use a fractal algorithm to generate the terrain for you. The benefits of this is that the landscapes can be extremely vast and be generated almost instantaneously, depending on the power of your computer or whatnot. You can have initial control points, so you can say, okay, well, I want a mountain here or a valley here, initially, and it'll make it without you actually having to do all the detail work. Um, the results can be extremely realistic, as we'll see in a few minutes, and it's much more fun to do this than to do it all by hand. And fractals are way cool. We're on, what is this, slide 3 now? Slide 4? The square
Slide 4.
the square diamond fractal algorithm is what I used to solve this issue. It was first demonstrated by Fournier, Fussell, and Carpenter at SIGGRAPH 1982, and SIGGRAPH is a convention for it's a special interest group for computer graphics. It's part of the ACM, or Association for Computing Machinery. It uses a series of fractal iterations to generate seemingly random-looking terrain. Similar algorithm used to generate the plasma patterns that you'll see in 2D packages such as the GIMP or Photoshop. It makes like the cloud texture. It's very very similar to this. And if you were to use the plasma patterns as height maps, you would come out with a very similar result. I don't know if it would be the same, but it would be very very similar. So we go on to the next step here. How it works. So this is the kind of the meat of the algorithm here. Basically, you have 4 points, the 4 vertices of a square, right? You average all of those points, and you come out with a middle point, and then you apply a little bit of variance in the z-axis of that middle point, so the height's a little bit different. And now you have 4 triangles, or half diamonds, right? And you basically need to make those triangles into full diamonds, so you add an imaginary vertex on the outside. The first step is the only step that you need to do this with. And then you just average the diamonds and put another point right there in the middle of the diamond. And so that'll give you points in the middle of the vertices of the initial, or it'll give you a vertex in the middle of the edges of the initial square that you had. And after the first square step and the first and the subsequent diamond step, you're left with, if you look at the little image I have there on the bottom, it's the third image to the right, where the first image is the initial square, the second image is the midpoint part of the square, and then the third image is after you put the midpoints of the diamonds down. And then you basically end up with 4 squares there that you can see. You have a top left square, a top right square, a bottom left square, and a bottom right square. And you repeat steps 1 and 2 on each one of those little squares. And basically you get this random looking terrain, or this very realistic random terrain, by applying a very slight random variance in the height for each iteration that you go. And it sounds complicated, but it's not. It's not really that bad. It's a fairly simple algorithm. Um, the random variance is actually based upon a value that you supply for the algorithm called the roughness constant, which is a value between 1 and 2. The roughness constant basically defines how much variance is allowed on each iteration. A larger value results in the random range decreasing a lot on each iteration, thus generating a very smooth terrain. That sounds kind of counterintuitive, but if you decrease the amount of randomness that you're putting into the terrain, then you end up with a smoother terrain overall. But if you only decrease the randomness a little bit each iteration, you can still get potentially very large differences in heights over very small distances because of that random range. And so you'll get stuff like cliffs or mountains and whatnot. And then basically the randomness kind of just, that random range tapers off as the algorithm, decreases or iterates and iterates and iterates. Okay, next slide. I basically made this using Python with Pyglet. In fact, I don't think I had any other dependencies. Everyone knows Python, obviously, and Pyglet is an amazing little kind of alternative to Glut. If anyone's ever done 3D programming before, there's this thing called the GL Utility Toolkit, which is terrible in every way. And Pyglet, what? Oh, it's widely known to be bad. It's well, no, I won't no, because just putting it out there to begin with, gave people the opportunity to use it and spread it and have it become as popular as it is today. But regardless, so Pyglet was it's probably the best 3D utility toolkit package I've used for Python. It just makes everything incredibly simple, and it's very object oriented, and it was literally a breeze to implement this. And so here's a demonstration, I'm on the next slide now, of what the completed algorithm can generate. And this is I think it's a 512 by 512 grid. It may be 256 by 256. But this is just one example, where you see there's a very obvious peak of a mountain right there in the middle that looks something like what is that, El Capitan over in Yosemite, and then you have nice little valleys in between there, and then you have these slight ridges and these dips and whatnot. It just looks very realistic, And this is with a roughness constant of like 1.2, I think, or 1.1 or something like that. So the terrain in general is very rough, and then you can also define your initial like random range that you want. So like for the first iteration, I think my random range on this was like 50 or 60, right? Which means that the random number that it generated at max could be about 60 or negative 60. And so you get, and then after the next step, the maximum random range goes from like 0 to, I don't know, probably 55 or something like that, because it's a low roughness constant. And so you just, you get stuff like this. And then I also have a video here. And I don't know if you guys see the video playing when I play it or whatnot, but it's basically just a YouTube video of the terrain spinning so that you get a full, 360-degree view of it or whatnot. And then I also send commands to generate new terrains on the fly. And you can see the terrains are generated relatively quickly. I probably don't have the best implementation of the algorithm out there, but even with my, my rough attempt at it, it still goes really smooth. Next slide. This is my obligatory quote. The best way to predict the future is to implement it, by Alan Kay. I'm not even sure who Alan Kay is, to be honest. He's like one of the founders of object-oriented programming languages or something. Uh,
I don't have a Mac though.
True that.
That's not a real programmer. No, I actually like Macs. I'm just messing around.
all right, and let's see what's on the next slide. Brought to you by Bixley.com and lots of Rockstar Lemonade. If you guys have not had this Rockstar Lemonade, it's fantastic. By the way, I honestly think I'm addicted. And this is the last slide. So, are there any questions? Yeah, so basically the grids can be a power of 2 plus 1 is how the algorithm works. So this is actually like a 513 by 513 grid. And you can also do a 257 by 257, etc. And so it's just one of the parameters that you pass into the algorithm, in my particular algorithm. Um, it can generate, any size map that you wish into whatever resolution that you want. Uh, Yeah, that's actually what I'm working on right now. There's actually, and I'm doing all of this in OpenGL, and in OpenGL, you can do multi-texturing, which basically means that you have like say, 7 or 8, or actually 3 or 4 textures applied to the entire grid or to the entire map, and then what I'm going to do is actually change the texture based upon uh, the slope of the particular that the vertex is on. So at the very level parts, there will be nice grass or whatnot, and at the steep parts there'll be rock, and I'll probably do some sort of altitude thing too, to where at the peaks of the mountain it looks like there's snow. Um, so that's currently in progress right now.
Pretty sweet.
Very nice.
So how long till we get to play this game, Ryan? Looking forward.
I'm working on it in my spare time, so we'll see. I don't know, a while.
Yeah, don't try
Right.
what Ryan's doing at home, kids.
All right.
Sweet.